I'm happy to introduce you today our host, our guest, Yannis Liodakis, that kindly accepted to give this seminar for us. And Yannis did his PhD at the University of Crete, and then he moved for a postdoc at the Kavli Institute for Astrophysics and Cosmology in Stanford. And actually, he works in Finnish Center for Astronomy. He has another fellow, and his research topics are multi-messenger emission of jets from supermassive black holes. And he have worked also on tidal disruption events, radio galaxies, gravitational lenses, and supermassive black hole binaries. He is particularly interested in multi-wavelength polarized emission, as we can see in this seminar. And he is the lead author of an XP discovery paper on Markarian 501 recently published on Nature. So before I let the floor to Yannis, I would remind for people connected that the questions are generally made all at the end of the seminar. You can raise your hand using the button. And okay, I let the floor to you. Thank you.
Thank you very much for the kind introduction. I usually let people ask questions during, but I'll follow the rules of the house.
Okay, you can change.
No, not the rule. I'll just follow it. So thank you very much for having me. And let me talk to you about supermassive black holes and what we can learn from them through polarization. I realize that my title is a little bit misleading because I'm not going to talk about all supermassive black holes. I'll be focusing more on the more violent or active nature of those black holes. And this is what we call active galactic nuclei. So this is a supermassive black hole in the center of the galaxy. You have a lot of gas around. The gas is accreted onto the black hole by forming an accretion disk. And about 10% of the time, you launch a very powerful, often highly relativistic jet that if it's on the plane of the sky, then we call that a radio galaxy for historical reasons. If the jet is oriented directly towards the line of sight, then we call that laser. And I'll be mostly focusing on lasers and radio galaxies because these are the most interesting, I think, objects. So this is what a typical radio galaxy would look like. This is the famous source called Cygnus A. And you can see the bright spot in the middle, that's where the AGN is. And you get this thin lines coming out. Those are the jets. And at the end of those jets, we have the radio lobes, which is basically where the jet terminates, starts mixing with the intergalactic medium, and it's for trucks. So if you focus on the AGN there, this is what it would look like. So this bright spot, we call that the core of the jet. In radio galaxies, it's more like the base of the radio jet. And what's coming out is the main jet. A similar but much dimmer feature you see there, that's the counter core, and of course what's coming out the other side, that we call it the counter jet. And somewhere between the core and the counter core, it's the supermassive black hole that is firing both jets. So now imagine you're an observer at the far side of the universe, and you're looking at Cygnus A from that side. So you're really looking down the barrel of the gun. And that's how we typically observe lasers. And most likely you'll see something like that. So as you can tell, we've now lost all this beautiful structure. We just get one bright spot. Here we still call that the core of the jet or the blazar core. It doesn't really correspond to the base of the jet anymore. It's a structure that's a few parsecs away from the black hole, and I'll tell you more about that. And you get a little bit of the jet because, of course, these are not exactly at 0 degrees to our line of sight. They're a few degrees off, so we get some somewhat position. And of course, you have also the intermediate cases, and you might be familiar with a source called M87, which is also the source that gave us the very first image of a black hole. And you can see how M87 looks like in different wavelengths, all the way from radio all the way to TV gamma rays, starting from radio on the left to optical and X-rays in the middle and X-rays and gamma rays on the right. Of course, the way the source appears has to do also with the resolution of your instrument, but at least for blazars, we're mostly observing them as point sources, really, with any instrument. We have other, of course, than PLTI. But whatever applies for MH7 should in principle apply for radio galaxies and blazars as well, if this is only a matter of orientation of that jet. So through a lot of work by a lot of different people, we have sort of a basic picture of what we think is going on in this jet, which is what we see here. So you have, of course, black hole and the accretion disk. You launch the jet. The jet is not very fast in the beginning, but it accelerates as it moves outwards by converting magnetic to kinetic energy. It goes through clouds of gas that we call the broadline region, which is what you see here, and we think is where the spectral lines we see in the optical are coming from. And then it keeps on accelerating until it reaches terminal velocity to a place where we call that laser core I told you about. The nature of that is not very, still debatable, but what we know for sure is that there is a lot of particle acceleration and high energy emission coming from that region. And after that, you're now at parsecs, into the parsecs away from the black hole. The jet can either continue with a constant velocity or decelerate, but you're now in regions where it's mostly dominated by radio. So if you compare this simple cartoon with what we see in M87, the structure, it actually matches fairly well. And in fact, if you study the shape of the jet in this M87, you'll see that as you're close to the black hole moving away, the jet follows sort of a parabolic shape. And at least according to the RMHD simulations, this is a shape that favors acceleration, which is what we expect to happen very close to the black hole. And then you reach about the boundary radius, which also happens to be around that laser core. And the boundary radius marks the sphere of influence of the black hole. And after you cross that sphere of influence, the jet changes its shape and becomes conical. And again, according to the simulations, conical shape doesn't favor acceleration anymore, which is basically what we're expecting from the cartoon. And in fact, there was a recent study looking at nearby radio galaxies, and they basically saw the same change in the jet shape. And I'm just showing you one example here that goes again from conical, so from parabolic to a conical job. So we think this is sort of a common occurrence in this jets. And as you can tell, we're doing fairly well with the structure, and we're understanding a lot of what's going on. Where we don't really understand much is radiation. And if you look at the spectral energy distribution from different blazars, they all pretty much look like this. So they have two broad emission components, or two pumps, as we call them. The first one comes from relativistic electrons that have been accelerated in the magnetic field of the jet and make synchrotron. We use the location of the peak of that component to classify blazars into low, intermediate, and high signature peak sources, depending where that peak is in the infrared, optical, and X-rays. That will come in handy in just a moment. What we don't understand here is basically how the particles accelerated in the jet to make that radiation. And we have two different scenarios for that. One is that we're looking at shocks, and this could be either shocks that are moving inside the jet. And in fact, when we look at the radio images, we do see radio components moving along the jet, or there could be standing shocks. And in fact, one of the scenarios for the nature of that blazar core is in fact that this is the first recollimation flow of the jet. The alternative is what we call a degree connection. And this is basically where you have opposite polarity magnetic field lines that will come together, break apart, and then reconnect. And then you accelerate particles along those reconnection lines. The high energy pump that goes from X-rays all the way to TeV. That we don't really know where it's coming. But again, we have two possibilities. One is that we're looking at what we call photonic emission. This is basically inverse compton scattering. So you have electrons moving in the jet. They see some target photon field that could be external to the jet. It could be a accretion disk, the broadline region, or some other structure. And the electron will see that those photons and scatter them to higher energies. And we call that external compton. You can have also photons coming from the jet itself. So the electrons will make the photons, and then they will scatter them to higher energies. That's called synchronous subcompton. The alternative is what we call hadronic processes, and this is now where you have protons in your jet. Protons will make synchrotron, or they will interact with other protons, or other photons make pions. Pions then decay to secondary particles and gamma rays. So learning about the origin of this high energy component tells us also something about the composition of those jets, and this has been sort of a very interesting and hot topic lately, because IceCube, which is a neutrino observatory in the South Pole, recently, not so recently now, in 2017, detected a high energy neutrino coming from the direction of a blazar called KXS 506. Now, that association is not solid, and there's still many questions whether, where the neutrino would be produced in the blazar and how. But you can imagine if you sort of associate blazars with high energy neutrinos, you open up the way to maybe understanding what's the origin of ultra high energy cosmic rays. And then now you're entering a regime where things become interesting for particle and fundamental physics in general. So that has been a very sort of interesting and hot. So whatever happens in those jets is really driven by the magnetic fields. And that's why it's very important to use polarization to study them, because we can trace those magnetic fields with polarized light. So I'll tell you a little bit about what we're trying to do in the optical and of course X-rays on that front. And I'll start with the optical. And I'm part of a group called Robopol that we've been systematically now studying blazars for a few years using a novel polarimeter, which we also call Robopol. And we see sort of the design here is what we call a one-shot polarimeter. So it allows us to obtain all our polarization information in a single exposure, which is not normally the case for those not familiar with polarization. That makes it very accurate and very efficient instrument for monitoring. So we're using the 1.3 meter telescope at the Liodakis Observatory there, and that tiny instrument is the polarimeter. So it's actually very compact and around. So this is the observatory, and the lights you see down there, that's the city of Iraklion, which also happens to be my hometown. So of course, if you have a good polarimeter, you're not restricting yourself to one science case. And over the years, we've done quite a bit of other projects. I don't have time to go into this, but you're more than welcome to ask me about them if you see something interesting. So our primary objective with Robo was to understand the sort of peculiar and unique phenomenon that happens in blazars, which we call the rotation of the polarization angle. So normally the orientation of the polarization on the jet will just fluctuate randomly until at some point it will stop doing random things, and we see smooth monotonic rotations of the polarization angle, which is what you see here in the middle panel. And then when it's done, it goes back to fluctuating around. So before we started our project, there were only a handful of these events known. So we didn't really have any statistics to do anything with them. And the key question was whether those are real. So you can imagine a situation where something happens in the jet and drives a change in the magnetic field, and you see that as a rotation of the polarization angle. But you can also imagine a situation that in the randomness of things, you just happen to go towards one direction in your random walk, and you create that apparent rotation without anything physical. So our first task was to actually increase the number of rotations, so we actually have something to work with. And in fact, in just a few years of observation, we're now more than tripled the number of node rotations. And the second step was to actually try to understand whether there's a connection between these rotations and gamma ray activity, and particularly gamma ray flaring. And the reason for that is that, if you can associate gamma ray flares with the rotations, you have to have a common mechanism that drives both. Right? So there's no longer random events. So our very first result in this direction was actually came with our very first observations, was the fact that the sources that have been detected in gamma rays are more polarized than the sources that are not detected in gamma rays. And there is really no good reason for that to happen unless there is actually some connection between the polarization properties and gamma ray activity. But in order to address the question about the association with the flares, we basically took the gamma ray light curves, and you see an example of that here, and then you find the peaks, which basically mark, the flares in gamma rays, and you try to estimate what is the time difference between the rotation we detect in the optical and the peak of that gamma ray flare. So the rotation is shown here in this pink line. So we get the middle point of the rotation and estimate how far it is from the peak in gamma rays. And if you do that for all the rotations we have, this is what you get. So the y-axis shows you it's the normalized amplitude of the flares. It's not very, very important. What's important is the x-axis here, which shows you that time difference. And as you can see, they're all pretty much centered around 0. So every time it would detect a rotation, there was always a gamma ray flare. And that is actually very hard to do by chance. So if you just throw rotations in the gamma ray light curve randomly, you will not get this good result. So there must be some common mechanism that's driving both, EVP rotations and gamma ray flares. Of course, individual events could still be random, but as a population, they have to be, most of them are physical. Now, exactly what is what's the mechanism behind the rotation is still unknown, but we're working on that, and I'll tell you a little bit more about this later when I talk about X. Another very interesting and sort of not very intuitive result, this in the beginning, is that we found that the sources which their synchrotron peaks in the infrared tend to be more polarized than the sources that their peak is in the X-rays. And again, there is not sort of very obvious reason for that to happen. The way we try to explain this is that you have a population of electrons that is evolving. So imagine you have some acceleration site here that could be either shocks or magnetic reconnection. It doesn't really matter. What matters is that you take a population of electrons, you accelerate it, and then you affect it. So the high energy radiation, what makes everything from the peak and to the right side of your spectrum, that comes very close to the accelerator with a more ordered magnetic field, and it should be highly polarized. Then the electrons will move down the jet, they cool down and make lower and lower energy radiation, and that makes everything from the peak and to the left. And now this comes from a much larger volume of the jet, sees more tangled magnetic field, has to be less polarized. Because we're looking at the fixed frequency, right? So we're observing in the R band in the optical. For the LSP sources, optical is in this side, so it should be high polarized. For the HSPs, optical is in this side, it should be low polarized, and you can explain that. So we made two predictions back in 2016. One is that the HSPs should be much more polarized in the X-rays than in the optical, and that they should have rotations of the polarization angle much more frequently than we see the optical, or at least sort of the same that we see. And just a couple of years later, Fabrizio Tavecchio actually did the proper simulations, considering both the shock and the magnetic connection region, and he got basically the predictions of what we expect to see. So we had everything we needed to test this scenario, but of course, back in 2016, there was no X-ray polarimeter. So there was no way to test that anything we said was fine, because you could not check whether we're making things up. But fortunately, times change. And since just last year, we have our very first X-ray polarimeter. It's called, of course, the Imaging X-ray Polarimeter Explorer. It was only possible through technology that was actually developed in Italy. So you have to be very proud of that achievement, and we're very thankful for that. And it's a small NASA mission. It has a 2-year lifetime and operating 2 to 8 kV back. So I decided to go up against my own best interest, and I led the study to select targets for the observation that we're doing now, which is what you see there. So the y-axis shows you the predicted X-ray polarization degree. That, of course, came from simulations because at the time there was no observation. And x-axis shows you the X-ray flux, which was observed by SWIFT and other satellites. The red dashed lines show the XP sensitivity for different exposure times, and for the color and the different sources are just different symmetric classifications. So I can tell you already that this is actually proven to be a fairly accurate figure, both in terms of what the sources were doing and the XP sensitivity. Of course, we're not just observing blazars. There are 7 different topical working groups. We're basically observing anything that is bright in X-rays and we think is polarized. And of course, there are many people even in this room involved in several of these groups and Rome in general. So this is really, if you're interested in that, is really the place. I'll of course tell you a bit more about Group 7, which is blazars and radio galaxies. And after the mission was launched, I'm now coordinating all the multi-wavelength follow-up for the IXP targets, for the blazar targets, which, as you will see in a minute, is really crucial to help us understand our data and interpret them. So our very first observation was actually a radio galaxy called Seminari, and this is what you see here. So again, the core is sort of near the base of the jet, near the black hole. And we get a little bit of the jet sticking out, and of course, because IXP has a large field of view, we get the ULX here for free, basically. So as you can see from the archive numbers there, we have a few of the papers already out, and there are more coming. So I'll tell you about those results mainly, but I'll also mention stuff that are not being published yet and stuff that are under embargo. So for the remainder of my talk, please no pictures or social media of any time, because we're going to get in trouble. So the 2 main sort of key science questions we wanted to address during these 2 years is, first, of course, what is the origin of that high energy component, and by extension, as I've told you, what the jets are made of. And the second key science question is, of course, how particles are accelerated, and finally differentiating between the shocks and magnetic information. So for the first question, we really want to use the low signature peak sources. And this is because you have optical on the first hump, which is synchrotron, and X-rays are all part of the second hump, which is something else. And those are the sources you see there in black. And there I've assumed that we're looking at electrons and inverse quantum scattering. If you assume some hadronic process, you get the blue points, which, as you can see, are much more polarized. So just to give you a rough approximation to have a mental image in mind, if optical is more polarized than the X-rays, then we're most likely looking at electrons and inverse quantum scattering. If the X-rays are about the same or more polarized than the optical, we're most likely looking at protons and some hadronic process, just to have some rough. So the very first source we observed in this category is a famous one called VLAC, and you see here the results of the optical campaign. So the top is brightness, then polarization degree and polarization angle, and you can see VLAC is a very variable source. We had 2 observations in the first season, one in May and one in July. You can see that in the gray shaded areas. That basically gives you the duration of the IXP observation. Unfortunately, we couldn't get a detection in either, but we got pretty good upper limits from anywhere between 6 and 14%, depending on the assumptions you make during the event. What is interesting here is that if you assume the pessimistic upper limit, then the optical seems to be more polarized than the X-rays during both of the observations. If you assume now the pessimistic upper limit, 14%, we still see the optical be higher than the X-ray, especially for the second. Of course, there are details here that I'm sparing you, so we cannot be very, very conclusive, but it really looks like that we're looking at electrons and inverse complex scattering. Of course, you want to have more sort of more sophisticated and better tests of these emission processes. And this is something we try to do with Lawrence Pearson, who's a graduate student at Stanford, using some of the multi-zone jet models that he's been working on. And the idea here was actually to look at intermediate peak lasers. And the reason for that is, at least for some of the sources, the X-rays happen to fall sort of in between the two emission components. So what I'm showing you here on the right is actually three different sources. The first four panels are two sources in flaring and quiescent states. These were potential IXP targets. And the last source here, that's TX506, that's the source that's been associated with the neutrino. Unfortunately, this is too faint for IXP, but it's an interesting source. So the idea we had was to do first the full polarized modeling of the SED and try to understand how polarization behaves across that tip. And the second was to take the IXP band, which you see here in red, and place it in such a way where the lower half of the energy range will be dominated by the first compound synchrotron. So we're looking at the extreme end of the synchrotron spectrum. That should be highly polarized, and that will give us a detection. But the high side, the high energy chunk of the IXP band, that would be dominated by whatever is making the second component. Now, if that's a hadronic process, it should be polarized. We should get a detection. If this is an electronic process, then it should be far less polarized than the synchrotron, or even unpolarized altogether. So we should not get any detection. So whether you get detection or no detection, you can maybe say something stronger about what's happening. So on a normal day, BLAC that I told you about is like this source. So basically, all the X-rays that IXP is measuring is at the high energy part. But when BLAC is flaring, the synchrotron peak moves to higher energies. So basically, that very tail end of the synchrotron peak will move into the X-ray, into the XP band, and it will turn into one of these intermediate peak sources. So we were very lucky that just November of last year, so a few months ago, BLAC went into an outburst, and we saw that change in the spectrum, and we triggered our observation. So this is what you see here on the left. This is our X-ray campaign with XMM and U-star. And you see sort of the curvature you get in the spectrum. And this is exactly because that synchrotron bump is moving in. So on the right, you see the first three panels are the optical campaign. Again, brightness, polarization degree, and polarization angle. The bottom three panels show you the same thing, but with IXP. Of course, we don't have the signal to noise to do a same fine job as we do in the optical. So we have to split in just three bands, but it's actually more than enough. And in fact, only the first chunk there is the interesting one, because this is when the synchrotron component actually dominates the low energies. So if you limit yourself to 2 to 4 kV, so just split the band in half, then you get the blue point there, sorry, the red point there, and that's a significant detection of about 20% polarization. So we're really looking at the extreme end of that synchrotron spectrum for the first half. If you do the full energy range, if you do 2 to 8 kV, you get the blue point, which is no longer a significant detection. And that's telling us that whatever is making up of the second component, it's most likely unpolarized, or at least far less polarized than synchrotron. So again, there are a few caveats here, but I think now the evidence are piling up that we're really looking at electrons and inverse complex scattering, at least for that part of the. For the second key science question we try to address, which has to do with particle acceleration, we now need to use HSP sources. And that is why we have both optical and the X-rays part of the same hump, and you're looking basically at the same mechanism. And this is the ones you see, the sources there in green. So just before the mission was launched, we told the satellite people that 100 kiloseconds gets you Markarian 501. And actually just a year ago, now, so in March of 2022, at 100 kiloseconds later, IAPS detects X-ray polarization from a supermassive black hole for the very first time. And this is what that is. So that's the Stokes U and Stokes Q. That's actually how the parameter we use to measure polarization. So what this figure is showing you is that there is a 10% polarization, which is roughly aligned with the jet axis on the plane of the sky, which is that magenta shaded area. Of course, that being the first observation, we had to do a second one to make sure, and that happened just 2 weeks later, and we basically got the same results. So again, another 10% polarization, roughly aligned with the jet axis. You might think the angles are different, but they're in fact within 3 sigma, so they're different also significant. Of course, 10% doesn't really tell you anything. You need to put that into some context, and again, this is where the multi-wavelength campaign comes very handy. So what I'm showing you here on the y-axis, that's the logarithm of the ratio between the X-ray polarization and the optical. And the lines I have there are expectations from different models, from anything from there is no change between the optical and the X-ray polarization to the gray shaded area, which is that energy stratified model that I told you about, where we expect much higher X-rays. That's the only thing. And in fact, we found 2.5 times higher X-ray polarization for the first observation, and of course the second observation just confirmed our results. What is very interesting is that we didn't only have optical, but we had radio polarization as well. So if you put that together, we found that there's a near exponential rise in the polarization degree as you go from radio to optical to X-ray. There's a nearing doubling of the polarization degree with every step. And if you look at the angles, then we see that they're all sort of roughly aligned with each other, and all sort of roughly aligned with the jet axis on the plane of the sky. And that's very useful for the interpretation. So you can write down all our different expectations for the different models in terms of multi-wavelength polarization and angle variability, and compare that to the observed. And there is in fact a model that satisfies all our observations, and that is when you have this energy stratified electromodulation, but one that's accelerated by shocks and not magnetic reconnection. So even with the very first observations of IXP, we're able to satisfy all our, at least for the one objective, all our goals. Now you will reasonably argue that this is only one source, but since March, I have actually observed many other HSPs multiple times, and we're basically getting the same results. So this is the second source we did, of Markarian 421, where we found that the X-rays were 5 times the optical polarization. So even higher, the angles are still sort of consistent with each other. This time they seem to be a little bit of axis, not a lot. It's 3.1, 3.2 sigma. So it could be that we're looking at some bend in the jet, or it could be that we're not really determining the jet angle on the plane of the sky very well. These sources are not very bright in radio, so they don't really make a good VLBI targets. So it's really nothing to worry about. What I think is very interesting is this dashed line there, and that is a very simple calculation of how polarization will change as you move away from the shock prone and let turbulence take over. And as you can see, it goes through the observations very well. It's obviously not perfect, but for a simple, almost back of the envelope calculation, I think it's really as good as it gets. So we are fairly confident that at least the steady state emission from the sources comes from shocks and this energy stratified electron. But we had made a second prediction from the optical, and that is that these sources will be showing rotations of the polarization angle. Of course, when we, before the mission was launched, we were discussing this, we thought that was impossible to find. That would be very sort of a miracle that we actually managed to catch one. So after the first observation of Markarian 41, we had two more back to back in just a month later. So we had two observations with just a day gap. And then when we got the quick look analysis from that, it showed that the source is completely unpolarized. So you can imagine that raised a lot of red flags, a lot of alarms. People started to panic. Like, how can you get a very highly polarized source suddenly become unpolarized? And then you, of course, have to realize that the quick analysis just takes everything, puts it all together, and assume that nothing changed during your observation. Where in fact, if your polarization angle is changing, you end up averaging over different polarization states and you cancel out all the polarization. So in fact, we were observing our very first X-ray polarization angle rotation. So the top panel shows you the polarization degree in both radio, optical, and X-rays, and basically nothing was changing. But when you look at the angle, you see this really, and I cannot stress how beautiful I think that is, EVP rotation in X-rays, whereas at the same time, when you look at the optical and radio, nothing was really happening. And that is actually something we sort of expected in this scenario if the X-ray emission region and the optical are not exactly co-spatial. So you need some time for the electrons to cool down to make optical, and that means that they moved a little bit away in the jet. So if we kept monitoring the source in optical, maybe we could have seen something happen there. Unfortunately, we did not know this at the time, and we just stopped our observations when IXP stopped observing, so we missed our chance. But we now know. So maybe next time we'll be able to capture that. And very recently, just in February of just a month ago, we observed a different HSP source called PG5053, and we've actually observed the opposite sort of behavior. So this is again the optical follow-up, the optical radio follow-up of the source, again brightness, polarization degree, polarization angle. And we had two observations with about a week in between. Unfortunately, the second one was cut very short because of a QO. But this time, if you look at the bottom panel here, we see a rotation in the optical. So it actually looks like it started before the IXP observation and sort of continued until the second observation. Again, if you look at the radio, which shows in these blue points here, nothing is really changing. In the X-rays, this is something we're still working on, and this is very preliminary results. So take them with a grain of salt because we're not done with our analysis. But basically, the preliminary results indicate that there was not really anything changing in the X-rays as well. So it could be that if we had observed with IXP just a week before, we might have caught another rotation. But yeah, we'll not know. But it definitely goes in the direction that, again, the X-ray, optical, and radio emission regions are not one, are not exactly the same, but you get emission from all the jet, not some localized. So just to summarize, I hope I convinced you polarization can be very important in our understanding of the sources, and I cannot stress enough how exciting I am personally, but I think all the laser community about having X-ray polarization finally. We're really solving decades-old questions with just the very first observations of IXP, not just in lasers actually, but in all the other sources that we're observing. And of course, this is only the beginning. We have another year of observations ahead of us, and of course, if we're successful, and we've been very successful so far, it's very likely that NASA will give us a guest investigator program. So we'll not only prolong the mission, but it will make it a community instrument, so everybody can apply for the time and do your assignment. But in terms of lasers, at least, I think we're fairly confident that the steady state X-ray emission comes from shocks and it's energy stratified. And we're still a little bit working on it, but it really looks like the high energy part, at least the X-ray part of that high energy component, comes from electrons and neutrons. Thank you very much.